All right, predictive analytics, forecasting with regression. To what extent can current data be used to generate valid predictions of future outcomes? So an instructor wants to know if shoe size can be used to predict exam score. The instructor collects data from 30 students on their U.S. shoe size and their most recent exam score in percent. Using this sample, the instructor wants to determine whether shoe size is a significant predictor of exam score at a significance level of alpha 0.05. So here, in terms of prediction, we're really concerned about that trend line, because the trend line is going to allow us to predict future values. And if the true slope, beta 1, right, is 0, so the true slope in the population, if the true slope in the population is 0, then most sample slopes that we calculate off that population will fall close to 0 just by chance. Occasionally, random samples will produce weak positive or negative slopes, but strong slopes are unlikely if H0 is true. So we're trying to find out whether or not there is a predictive element in the sample that's strong enough for us to conclude that it could be used to predict in the population. So we're doing simple linear regression, and our null hypothesis is that the slope in the population is 0. In other words, it's a horizontal line. Otherwise, it's not equal to 0. And what are we predicting? We're predicting exam score, and we're trying to predict it from shoe size. Seems unlikely, but who knows? We'll find out. So let's do a little test on our Greek knowledge here. We've got statistics and populations. So from the mean, the sample statistic is called x bar. For the population, it's called mu. The correlation for the sample is r. For the population, it's called rho. And for regression, the sample is b. And for the population, it's beta. Okay. So our assumption is that beta is 0. And now we're going to find, well, what actually is the slope if we graph this data? Now, we could calculate it with Excel functions, but as you can see here, this DATP means that we're actually going to grab all this data from the data analysis toolpack. So, and we're going to place all that over here. Should have given you a spot to place it, but try to place it well, actually, I am going to give you a spot to place it because it's actually very important where it's placed. So on your copy, this will be clearly indicated. Okay. So we go to data analysis, regression. The Y is what's being predicted, which is exam score, including the heading. Why the heading? Because I'm going to check this box for labels. And the X range is the shoe size. Confidence level is 95%. That's our alpha, 5%. And the output range, hopefully I get this right. Put it right there. Okay, so that now we can go ahead and grab some of this data. So we need the coefficient is the b. And so that's the slope. And the question is that a big slope? Not so big a slope? We'll find out. And the sample size is here. That's the number of observations. The R squared is in the DATP2. It's right here. If I'm not making you dizzy going back and forth. And now we need the standard error for the coefficient. And this is tricky because there's two standard errors in this output. There's one up here for the whole model, but there's another one down here for the coefficient. We want the one for the coefficient of shoe size. And the significance level from the problem is 0.05. So we type that. Okay. So we take the alpha and we split it. And the t-score, instead of calculating it, we're going to pick it up from the data analysis toolpack, and it's going to be the residual degrees of freedom. Well, actually, we are going to calculate it, and then, but using the residual degrees of freedom. So t dot inverse this probability, and then we'll pick up the residual degrees of freedom. Do the same thing here, except it's not this probability, it's 1 minus that probability because it's on the right side, and then the same residual degrees of freedom. All right, and then our slope over here is beta 1, or B1, sorry, is going to be t times the standard error. Kind of similar to what it was in the correlation problem. T times the standard error. The same thing here. T times standard error. And then our test statistic, we start out with that slope. And then the question is, okay, that slope has a t-score of what? Well, that's actually given here. There it is. So we just type start with an equal sign over here, and then go grab it right there, the t-stat. And the p-value is also given over here. It's this guy, but we're going to divide it by 2. So we say equals that guy, but then divide it by 2 because it was a two-tail test. And this isn't taking account of that. Okay. So there we are. And as you can see, we do not fall in the rejection region. So in other words, that slope is so weak. And if you think about it, it is not a big slope, right? 0.97. That we do not conclude that we actually are able to fail to reject the null hypothesis, and we can assume that the true population slope is 0. But be that as it may, since you need to know how to do this when it is significant, I'm still going to fill in all the questions here, even though, truthfully, this prediction table is meaningless once you decide that you're going to fail to reject. But like I said, I'm going to fill it in anyway, so that you know how to work a problem where it is significant. So the estimated exam score here, right, because we actually were trying to do predictions for other shoe sizes over here, is going to be equal to the intercept. Let's go grab the intercept. Plus the, and since that's going to be copied, I probably should lock that. Intercept plus the slope times the shoe size. Lock that too. Times the shoe size. And copy that down. And then we do that plus 2 times the standard error sorry, the standard error. Oh, and you gotta lock it. So that gets locked. Okay, apparently it's not enough. So it's going to be this guy plus 2 times. Why is it unhappy? Student error. Oh, sorry. Okay, so I made a classic mistake. So this standard error applied to the coefficient, the shoe size, but this is predicting for the whole model, so we actually have to use the other standard error, which is this one here for the whole model. And that actually does have a different value than the standard error for the coefficient. So that's the one that we need to use and lock it. And then copy it down. And over here, we do a similar thing, equals that minus 2 times this locked standard error. Copy it down. As you can see, the slope is negative, so we're actually predicting that as shoe size increases, exam score goes down. But again, we're doing this just as an academic exercise, because the truth is we wouldn't fill out this table at all once we've decided that we're rejecting the, so failing to reject the null hypothesis, because there is no predictive power. Okay. Here we report our alpha. And then we have our p-value. If we grab it from here, we don't have to divide by 2. If we grabbed it from the output, we'd have to divide it by 2. Here we've already, up there we've already divided by 2. And our p-value is bigger than alpha, which is why we fail to reject. All right, and what our lower t-score is that one. Our upper is that. Our test t-score is here. So it's less extreme, right? It's actually between these two. So it's less extreme than our cutoffs, critical values. And so it falls in the fail to reject because it's between the two. And so we fail to reject the null hypothesis. Then over here, if we fail to reject, then the null hypothesis is that the rejection of it. Okay, what's the correct conclusion? Slope is not significantly different from 0, and shoe size does not predict exam score. So we're saying that the true population slope is 0. No relationship. Statistically non-significant. And what was trying to be estimated was exam score, even though we couldn't. Okay, the predicted value. What's the intercept? Well, the intercept we get off the DATP. Can you expect for every shoe size? How many exam scores can you expect? So this is simply the coefficient. If it were predictive, it's not. So again, in a problem where we reject the null, this would be meaningful. It's not really here. What's the standard error? And that's this guy up here. That's for the whole model, remember? Is due to the difference in shoe size. What percent of the difference? That's going to be the R-squared value. Again, if it were true. What exam score would be predicted for a shoe size of 14? So you find 14, you predict an exam score of 70. And for a shoe size of 0, which obviously doesn't really exist, but remember, this is where you get the value of the intercept when the coefficient is 0 in the equation. So if shoe size was 0, then this term goes to 0, so you're left just with the intercept, which is this guy. And what's our average prediction error? That's the same thing as the standard error. So just asking the same question in a different way. And for a shoe size of 15, we can be 95% confident to see between 53.2 and what exam score. So we find 15, there's the 53.2, just round it off here. And so it'll be this one at the upper bound. In a scatter plot, which variables are normally placed on the x and y axes? X is the dependent, X is the independent, and Y is the dependent, because Y depends on X. And the R-squared that we mentioned just a little while ago is how much variation in Y is due to X. Great. And I think we're all done. Good job.